Hi everyone, my name is Nicos Georgiou and I am a reader in probability theory at the School of MPS. And I am really happy to welcome you to my lecture, which the title says it's about mathematics, but I will fix that in a second. As part of the online reunion for the 60th alumni reunion weekend. During the 60 years of Sussex, we have been promoting and celebrating the amazing work of the university. The math department has been really active um, in our work, and the alumni reunion weekend is the event in which we wrap up an incredible year of celebrations. And I really hope you enjoy my lecture. If you manage to stick until the end, there is going to be a magic trick which I am pre-advertising. Um, but of course, this is a pre-recorded lecture, so God knows how the magic trick will go. So I am going to talk about how to spot mathematics around you. Before we start, I would just like to show you my face. That's me. In that particular picture there, I'm actually talking about connections between mathematics and a zombie apocalypse. And like I said I'm going to talk about mathematics, but I will fix that right now. First of all, I'm a theoretical mathematician, so I'm going to tell you how to spot theoretical mathematics around you. Now, in general, the theory is really difficult to find unless you have it in applications. So in the end, I will talk about how to spot theoretical mathematics in applications around you. But again, that's a bit too broad, and in mathematics, usually we specialize a bit more. So I will switch that into my particular area, which is probability. So in the end, this talk, now the correct title is How to Spot Theoretical Probability in Applications Around You. So before I start discussing probability with you, which can be something, randomness can be really complicated in general for the human brain, as I will explain. I want to talk to you about the general research area that we do here. We have four main research areas in the department in its current version. The first one is analysis and PDs. In the figure here is the figure there tries to answer the following question. Essentially, if we have a shape and we squish it down symmetrically, do we change the perimeter and do we change the area or not? We have a large group in numerical analysis and scientific computing. In the most basic of examples, they try to answer the following question: how do you know that your calculator gives you the correct result? So you need some kind of numerical analysis behind it for that to be the answer to be it's always right. We have a group in math biology. What you see in the figure there is some virus. I think I stole this for a COVID picture, but of course it's a standard picture of anything. Biological models can be studied mathematically and in a rigorous way. And it doesn't mean the model is going to be 100% accurate, but it does mean that the main features will be captured. And finally, my area, which is probability and statistics. I am a theoretical probabilist. I'm not going to discuss this picture, but maybe it will come up in some form later. So since you guys are alumni, this is the newest information we have for you in terms of our research. In our Research Excellence Framework 2021, the quality of our research papers came up 17th in the UK, which we're really proud of. And please feel free to contact me or my colleagues if you are interested in any of these research areas for whatever reason. We would be really happy to talk to you. We do a lot of outreach events. We do a lot of public engagement events. Now, I would like to convince you first that mathematics is all around us, even though it's not immediately clear how and where. And some of the issues I will bring up may sound frivolous, like, for example, puzzle books. But of course, if you have a puzzle book that gives you a bit of fun, considering the 3 years that we just had with lockdowns and so on, maybe it's not such a bad thing. And a lot of the puzzles, particularly the one you see in the picture, the Today program puzzle book, has a lot of puzzles that can be solved using basic maths, even or just logic, really. Um, Mathematics appear in gambling, and there is an article whether Theresa May's Brexit deal would have survived. This was well before we knew what was going to happen. It can help with disease outbreaks. And again, you can see the date. This is from 2018. We didn't know what was coming when we were writing that. It could be something as understanding cues, which I will talk a lot about in the sequel. And it could be about opinion polls. All of these things, data analysis, probability and statistics, operational research, math biology, gambling, they are all things that we experience in everyday life, and theoretical and applied mathematics can actually attack them in various ways and give insight and understanding. All of these articles can be found in the conversation, so feel free to Google them. Irrespective of the fact that I am an author in all four of them, they are a great read, trust me. Okay, so just to reemphasize, all these math, they started research. They started at the research level before they were well understood to become and go and become on the applied level. And then the theoretical research has limitations. There are theorems that need to be proven rigorously, but those may not completely apply to reality, and that's where applied mathematics come in and tries to understand the models at a different level. And everything is synergistic in this sense. So, like I said, I'm a probabilist. I will try and guess what you guys think when you hear the word probability. This is the picture that I advertised my group with. But I think we can all agree that whatever this pic may show, when I say the word probability, this is not what people think. Perhaps the most common thing that people think when they hear probability is actually a different area, which is statistics, which is useful, but it's totally different than actually thinking of the theory of probability. One informs the other. The problem of one requires the other to prove theorems, and then the theorems are used to decide if they can be applied for the statistical problems. And again, statistics, we hear a lot about data and statistics and so on, but usually when people think of probability, they actually think of gambling, coin tossing, the roulette, dice, or even card games like blackjack and poker, which have also a different set of skills, not only pure chance. Now, if you are a bit older, maybe you may have heard of the Monty Hall problem. This used to be a TV show, and the host, Monty, presented the player with 3 doors. One door has a car behind it. If it's selected and the player wins the car, the other 2 doors have goats. And the game would go something like, please pick a door, player picks a door. Then, let's say they picked door number 1. Monty then would open the other door with a goat, in this case number 3, and then the player will get an option to stick with the door they selected, in this case door number 1, or switch a door and therefore go to door number 2, and then decide and then see what they want. So if they switch, in this case they would actually win the car. If they don't switch, they will win the goat. And this problem is very famous. You can Google it. It's everywhere. It has a Wikipedia page. You can find anything you want about it and why it's counterintuitive. And it was one of the very public examples that randomness is actually quite difficult to grasp and understand. But because it's so famous, maybe when I say probability, you guys think Monty Hall problem. If you are a bit more comic fans than me, like me, then you might know of the Scarlet Witch, and her superpower is actually manipulating probability fields, and they call that chaos magic or whatever you want to call it. But in the end, that's also one way that probability percolated into pop culture. So this is in general, I mean, I'm sure there are many other things that people think when I say probability, but I think these are the best of. So I would like to spend some time to discuss decks, which is something that almost everyone got their hands on at least once in their lifetime. And I'll tell you what can we answer rigorously. So if you open a fresh deck, every card is, every suit is in order, the numbers are in order. So essentially you can tell me, if I pick card number 37, you can tell me what card that is. So they are not shuffled at all. But there is some distance from that into having a deck that is so shuffled that essentially you are seeing a truly random arrangement. And we have a theorem that says that in actuality, if you want to find a random arrangement and see the deck in a random position, you need to do 7 not perfect riffle shuffles. If they are perfect, then you still know where every card is. If they are not perfect, then there are some variations, and as you go along, if you shuffle 7 times, the deck will truly look like it's in a random position. Now, a riffle shuffle is when you split the deck into 2 equal parts, and you make the cards slide into each other from one half a pack to the other half pack, and then you squish them together. So this is a theorem. If somebody tells you I have shuffled the deck and they didn't do it 7 times, then they didn't shuffle the deck. And if they know how to count, maybe you shouldn't trust them. So how many are the arrangements of a standard deck? I have 52 cards. The number of arrangement is 52 factorial. If you don't know what 52 factorial is, here's the answer. It's actually the multiplication of all numbers starting from 1 and ending at 52. So it's 52 times 51 times 50 times 49 up to 1. This is a huge number. This number has 68 digits. A million has 7 digits. And the last 12 of these 68 digits are actually 0. So this number is gigantic. And of course, when you guys see it like a 52 factorial, maybe it doesn't strike you as something spectacular. So let's see how spectacular this number is. First of all, 52 factorial is larger than the number of atoms in the known universe. Everything around you, if you break it down to atoms, it's still not going to be a number large enough to reach 52 factorial. Moreover, if you have every living organism in the universe shuffling decks, and in every second they show you what is the arrangement, the universe will cease to exist way before all possible deck arrangements become visible to at least one person. It's completely improbable that in our lifetimes we see, not improbable, impossible, to see all the arrangements of a deck. And that's why probability is important. It tells you how to tackle issues that we cannot see for sure. Let me put it in a different context. Let me tell you something that is truly improbable, and again, it's more probable than seeing the same arrangement of a deck. It is far more probable that 2 people in any room picked the same grain of sand at some point in their lifetime than have seen the same random deck arrangement. Of course, we have all seen a deck stacked, lined up, but if you claim that you have seen the same random deck arrangement with another friend of yours while not playing together, that is definitely less likely than you guys picking the same grain of sand uh, from some beach around the world. Now, decks have managed to enter popular culture in movies, particularly movies that have to do with poker or gambling. So let me give you some probabilities about royal flushes. The probability that you see a specific royal flush is 1 in essentially 2,600,000 hands. A royal flush is what you see in the picture on the top right, which is essentially an ace up to down to 10 of the same suit. So that probability is 1 in 2.6 million. If you don't want the royal flush, but any kind of flush, so 5 consecutive cards of the same suit, then that probability is a bit more manageable, is 1 in 37,260. And now with these numbers in mind, and how unlikely it is to actually see a royal flush or a flush, there is a lot of movies and series that actually give you a royal flush. So if you've seen these 6 movies, for sure you have seen 6 royal flushes in your lifetime, when the probability of seeing one is 1 in 2.6 million. So this is just to put in context how unyieldy these objects are and why probability is important in understanding whether somebody is cheating us or somebody is trying to cheat us and we can stop them. And of course, gambling is not my favorite aspect of my discipline, but that's how the discipline started. So it's good to mention it every now and then. But of course, people might wonder, okay, can you say something that is really useful? Not everybody is a gambler. So for the next couple of slides, I just want to tell you about probabilistic modeling and what it is we are actually doing with modern probability techniques. So first, let me give you the models, and then I'll tell you about the questions. So this is a coffee spill. I think this picture was taken when the coffee was spilled on a smooth surface. And if you think, again, coffee spill is a bit frivolous, here's an oil spill that actually was recent in all newspapers. You see, that's the red in the picture. You see it propagating down the river. And it's a random shape, the same with the coffee spill. Here's an epidemic trend. The black curve is the actual epidemic, the infected values, and the 2 curves, it's the worst and best case scenario in terms of averages. And the trend is that these things grow. Like that's the best we can say with this information. Then we can discuss random curves. Lightnings are actually random curves. They start at a random position in the sky, they fall at a random position on the ground, can we say, and then they sort of also spread out like in a webby kind of way. And we try to understand these particular random curves. Qs is a probabilistic model. What you see in the picture here is a queue at IKEA after the first lockdown. You can zoom in, you can see how many people were actually there and how they sort of waited there because the thing we do after lockdowns is really needing new furniture. And this is a simple queue in the sense that it's a first come, first served queue. Whoever is in front of you will always be in front of you. Whoever is behind you will always be behind you until you enter the building. So in this sense, this is a simpler queue than this one, which is a traffic. And in traffic, depending how many cars there are and how fast or slow the traffic is moving, you can switch lanes, you can bypass people, but you cannot really be completely crazy with what you're doing. And the final application or a final model is the end of times, like modeling a zombie apocalypse and how it will propagate. And again, you need some randomness because, of course, you don't know how the zombies will behave 100%. So what are the questions we're trying to answer? In the case of random shapes, we try to understand some properties about the shape. What you see there in red and white is more or less the average shape. That's an ellipse. And you can see that there is a bit of coffee outside the ellipse, a bit of coffee missing from inside the ellipse, but on average is an ellipse. In the case of the oil spill, that's only one ellipse. It doesn't cover the whole shape, but you can start stacking more and more ellipses, and then you can cover the shape, and you can still say something about this random shape. In the case of the epidemic trend, we care about the actual value versus the trend. The trend says growth, fine. The value says, well, if the black line is infected, when it reaches the peak, and this is an epidemic curve, it would mean probably that the hospitals will be overwhelmed. So growth is one thing, precise value is a different thing. Now, if you ignore the fact that I said epidemic here, and if I told you this is the Bitcoin curve, now it's far more interesting to know when the peak happens, because that's when you want to sell Bitcoin, for example, in order to make more money, and you want to avoid the crashes, which are the vertical down segments. In the case of random curves, my particular question is, why is that one tilted when everything else seems to be going vertically down, more or less? And why is that one not? Why is that an angle? How often does that happen? Is it important to understand that? The answer is yes. Of course, in the case of Qs, our questions are reasonable. We want to know when the Q is fast enough and whether we will reach our destination on time. And in the case of an apocalypse, we want to know when will the nightmare be over, essentially. When are we all going to die? If we don't die, how are we going to survive? Will we coexist? And all these things. Now, all these things are actually questions I cared about in my research. And I had to select one of these for you today. So I selected something that we can all understand, which is traffic. So I want to talk a bit about traffic. And what you see on my slide here is actually a road network. The red nodes suggest that there you have an option of which road to take to go down. So it's an exit if you think of this as a highway system. And I want to put a direction in my traffic. And let's say that we are all starting from the University of Sussex. And I don't want you to forget that's the university, so I labeled it. And let's say the goal is to reach somewhere in these locations in Brighton. And in order to reach these locations, we need to eventually pick a road to go down. And of course, there are many different assumptions one can make, but I want to think that somebody would like to visit these locations with some probability. I think somebody would want to visit the pavilion. I think somebody would want to visit the lanes. I don't think there is any forbidden location here. So if I'm talking about traffic, I want to say that the traffic will spread out depending where you want to go. And just to visualize the situation a bit better, suppose you are that last car over there, and in front of you there is all these other cars. And I want to understand this model of traffic. So can we say anything about how the traffic evolves? And the answer is yes. And this is some joint work that I have done with my collaborators, Nina Gantert from the Technical University of Munich and Dominic Schmidt, who is now at Princeton. And this was published in November 2021, so it's fresh out of the oven. And I am casting all our theorems in terms of traffic. Unfortunately, or fortunately, if you pick that paper, that's not how the theorems are stated. The application is more restrictive. The application to traffic is more restrictive than the actual model, which was what we call taste upon trees. So the first thing we needed to understand is whether we can find how many exits one needs to encounter in order to feel that traffic actually thinned out. So we used a very naive interpretation of what it means for the traffic to thin out, and we sort of assumed that drivers feel that there is no traffic in front of them if they are first in line. So assuming that you have n cars in front of you, when will we be possible? How many exits do we need to encounter, and when will it be possible to feel like we are leading the pack and there are no cars in front of us, like you see in the picture here. So in the picture here, every car is on a different street except the really last one that has still cars in front of it, but all the other ones completely separated, and we call this the disentanglement theorem. And this is something we can answer very precisely, actually. We need some assumptions on the speed limits, but of course we can always model that. And we also need to know how often you find exits and so on. But in the end, more or less, if you assume like you have 1,000 cars in front of you, you just need less than 10 exits to more or less be ahead of everybody. And if you want the mathematical sort of asymptotic, is that if you have n cars, then you need a constant time log n car exits to have this disentanglement. And if the speed limits changes, the thing that changes is actually the constant, not the logarithm. If these are city streets and the speed limits are all the same and they are quite short, well, the model needs to be adjusted, but again, it will be more or less this answer here. So this is the first thing. The second thing, which of course it's much more useful, is to understand whether we can predict when we have a total blockage. So a total blockage is something that looks like this. Cars move very, very slowly. They always have cars in front of them. The roads are all very busy, and there is no way to escape this. This can happen, for example, if certain segments of the roads are blocked by an accident, in which case the speed becomes zero and you cannot cross from there. So now you start having this bottleneck. But we can say in general when we can have this total blockage, and it depends on car speeds, speed limits. These can be made very precise. How fast new cars are entering the system. And it also depends how spread out is the traffic network, meaning how many options you have to escape into different side roads and escape this hell. But we can say when this can happen. And there are roads that we are finding that they are falling into this trap and creating these kind of things. We can also say the opposite. When can we go at maximum available speed? That's equivalent to near empty roads. We don't feel traffic if we are going at maximum available speed. And again, we have a very precise answer on what the speed limit should be and how fast the new car should enter for this to happen. But we can also sort of look into a specific area and try and see what is the local density of cars and whether it picks up at the later time in the day and so on. So most big roads are designed, big roads like highway system, motorways, they are designed with this in mind, and sometimes they work and sometimes they don't because the density of car changes. And of course, a far more important thing is to estimate, if you are at location A, how long it will take you to go to location B. And again, we can say something about this. Essentially, we need to argue how long it will take us to be the first in line, and after we are the first in line, we know we can go at maximum speed. So everything sort of connects in trying to understand the time to reach our destination. And this is just one application of probability that we all live through daily if we drive. Now, in the last few minutes of this presentation, and as I pre-advertised, I would like to talk to you, I would like to do with you a magic trick where I'm really going to try and read your mind, even though this is a pre-recorded lecture. Now, I may not be lucky with some of you, but bear with me. And after I explain what you need to do, pause the video, do it, and then let's see if I guessed correctly. So here is a bunch of random dice. These are truly random. I didn't throw them. I just asked a random generator to do it, and the image is a free perk. They rolled like this, and here's what I want you to do while I'm explaining the rules. You can start anywhere you like on the first line. The first line should have 11 dice. Pick any of those 11 dice and start from there. So in my case here, I started with 4. Maybe you don't want to start from that position when you do the trick. Just let me start from there. Now, I mean, of course you can if you want to, and if you don't trust me. This is a magic trick after all, you shouldn't trust me. But let's say we started at 4. So what's gonna happen is that we need to go forward 4 steps. That's the first one, the second, the third, and the fourth. And now we landed on a die that has the number 6 on it. Great. So now from the 6, we need to move 6 dice forward, and that will put us at that 2. And then from that 2, we need to move 2 dice forward. It will put us to 4, and so on and so forth. So repeat this, go forward down these 4 lines, go forward as much as possible. Eventually you will reach the last line. If you reach that 5, if you go 5 steps forward, you reach that other 5, and then you cannot move anymore. So the last 5, the last die of the whole arrangement, that's where you need to stop. Of course, you can also stop at that 5. There are not enough dice in front of it to move, so now that's the one you are going to stop. Overall, you need to keep in mind what is the die that you can no longer move after, and it's going to be somewhere on that last row, and just keep that in mind. And remember, you get to start however you like. So here is the slide with the dice right now. And at this point, I want you to pause the video. I will actually count to 3 to make sure you do it before I do anything. And do the whole thing. Move forward, start from a random position, move forward according to the pips until you cannot move anymore. And I will please pause in 3, 2, 1. Okay, so now if you haven't paused, you're being naughty. But if you did pause and you did it, I'm going to try and guess from which die you stopped on the last row. And of course, this depends on where you started. So let's see how many of you I'll get right, because mentalism is hard if it's done weeks in advance. But let's see. I conjecture that a substantial proportion of you, if not all, have landed on that particular 6. Now, if I got it, you might think I cheated somehow, and if I didn't get it, I can assure you you did something wrong. And in principle, I explained this trick in open days, but I will not explain it here. And if you really want to know how it works, just drop me an email. At this point, I would like to thank you very much for listening to my lecture. I hope that you found it interesting and learned some new information about probability and mathematics and what we are trying to do. And I hope that you continue to engage with the university and the alumni community. Thank you again for listening and spending this time with me. And I hope you have a great, great day.